right, welcome back. Hopefully everybody had a good spring break. Congratulations, everyone passed and is now in the next section of this 1230. So we're going to move into a few different components. So this semester, or this half the semester, we're going to learn a couple more techniques to make circuit analysis able to be looking at more complex circuits, to be able to simplify it and then analyze it that way. So there's going to be a couple more techniques you're going to learn. We're going to go into a little bit more understanding of the op-amp. So we only looked at it as a comparator before, and now we're going to look at it in different configurations and use it as a building block to actually create mathematical expressions. And so that's so those two things. And then the third thing we're going to focus on is going to be time-dependent elements. And with the time-dependent elements, there's going to be two components we look at. One's called a capacitor, one's called an inductor. We're going to look at them just like we looked at the resistor and how to use that, analyze the circuits that have those components, and also design with them. You won't have a final project in here because your final project will be in the lab instead. So this semester we won't have that final project portion, but we'll have the exams. We're going to have 3 exams. So on the syllabus, do note, if you forget when they are, do note these important dates. So there's going to be 3 exams this half the semester, and then you will have again that optional final retake option if you would like. So if you do well throughout this part of it, you'll be done by December 3rd. And if not, you'll want to take those exam retake options on the 3rd to increase your grade or make sure that you are showing that you've mastered the material. So the style will be very similar to what we had last half semester. And the only difference is this half the semester, I'm going to have a password to the quizzes for the daily quizzes. So just note those when I post them. If you want to start them as we're going, the daily quizzes are only going to be pretty much like more multiple choice, so they should be faster to do than the analysis. And then the end of the week quiz will be more of the analysis where you're actually going to solve the circuits. So do prepare for those and then take that by Friday. So that one will open up Thursday morning and be open Thursday and Friday. So just a slight difference on that. I'm trying to think if there's anything else. So grade-wise, it's going to be 80% are going to be the exams, and then 12% are going to be your attendance quizzes, and 8% is going to be that weekly quiz. And then they're going to be, again, 2% extra credit that you'll have throughout the semester. So those will be attending events, participating in different activities, and then at the very end, one of the extra credits will actually be to submit feedback for this semester. So, all right, any questions about what will be expected this semester, or this half the semester? Sorry, getting used to these half semesters. Yes?
Remember what we did on the first exam where if you failed it, you get put into a different section?
No, so this will be different. If you fail this one, you will have the option to retake the final. If you haven't performed well enough by then you'll have to repeat this next semester.
Are the exams the same format as last?
I know. You're having a hard time with the half semester too. I know. This is very new for me to do these half semesters. So yes, same format. It will be in the England lab. You're going to take the exam on paper, and then you'll put your answers into Canvas and then scan it into Gradescope. The only one will be the final. You won't, just because we have to grade those anyway, and so that will be the only one that will probably be different. All right, any other? Yes?
For the extra credit activities, is this all, like, only activities from this day forward?
Yes. Yes, thank you. So clarifying that, any department events that you go to, and note there's a nice new board that they have across from our study area that has a lot of different options. Any of those that you go to, you can get extra credit for throughout this next half the semester. The dates of those, though, will be from this timing until the end of the semester. will be when you would need to attend those. So those that were the first half only went towards the extra credit in 1220. Okay, and I do encourage you to attend as many of those social events, networking events. There is dissertations, which is good to see what other graduate students are doing and what research is going on here. Those are options to attend. We have amazing lecturers that come from all over the world that come and lecture, and those will be posted there too. So definitely encourage you to take advantage of those opportunities that are there.
Wait,
Yes.
do we just have to like take a selfie of us at the event, or like how do we like log in that we were there?
So you can either take a selfie or you can write a quick little summary of what you got out of the event, basically.
Oh, cool.
So, all right, any other questions? Okay. So for those, there's just a couple individuals that might be here that were not here last semester. Do go through that syllabus to make sure you understand, and let me know if, here we go. Let me know if you have any questions if you were not here last half semester. All right, so the quiz attendance today is called Superposition with a capital S. So that's going to be your access code. Again, you're welcome to, if you have your laptops or iPads, phone, whatever you want to open it. It is not timed for that one. So attendance is not timed. You can take the attendance as many times as you need to show that you have understood this material. It is a little bit higher level understanding with that multiple choice. And then Friday's quiz will be timed. So make sure you do note that Friday quiz is timed. Opens Thursday, closes Friday night, and that is timed for 45 minutes, and that will be working through problems. So Unit 1, practice problems are going to be very good to help you practice for that, make sure you're mastering that, and then take that quiz. Okay?
I used
Alright.
Unit 1 from this.
I'm sorry. I'm sorry, what?
Where's the Unit 1? Is it Unit 1 from this section?
Correct. Yep, so 1230 is a new Canvas page, so do make sure you're on 1230 and not that 1220 from last half semester. So 1230, Unit 1 will be the practice problems for this section, and then your attendance quiz on Friday will be these problems. Attendance quiz for today, again, is Superposition with a capital S, so you will need that access code to open it.
So to find these lectures, obviously you go to the 1230, but I'm just seeing the all modules from last semester.
Yes, so ignore that. The first homepage for some reason did not update when I changed the modules, so I'm gonna have to work on that. So go to the modules itself, and then Unit 1 on the modules, and I'll work on that homepage. I don't know why that homepage is acting that way. I saw that just a second ago when I pulled it up too. So this one should be Unit 1, Superposition, Thévenin equivalent circuits, and op-amp circuits. So that's going to be your first unit test, will be on those 3 topics. So today we're going to cover superposition and Thévenin. And so these techniques are to take a really complex circuit and reduce them down into simpler terms. So looking at superposition, while this isn't considered like super complex, you can imagine if you have multiple sources in a circuit, how that could look very complicated. So when you have different sources, there is a nice technique called superposition, and I like to use this analogy with the lights. So thinking about if I can figure out the lights. Okay. No, maybe not. Okay, so with lights, you have so much illumination when you have certain banks of lights on. So for example, you have just these 2 lights here. So it's pretty dim, but you have an illumination level based on those lights. So as I turn on different banks of lights, you can see like, yes, I get the contribution from the first set, and then I get an illumination that is also from the second set, all the way up to, I guess this is as far as it goes, to where it now is all contributing. If I turn one off and turn one on, I get that illumination. If I turn that one off and another one on, I get another illumination. When I turn them both on, I get the contribution of both of those. So this technique is basically the same thing as superposition. I turn off one, or I turn on one source, turn off all the other sources, get that answer. I turn that source off, turn on another source, get that answer, and I keep going with as many sources as I have. And at the end, I add up all of their contributions to give me a total amount. So that is superposition. So here's kind of a summary of those steps. So you zero out all but one source. And when I say zero out, when you zero out a voltage source, that means that you set V equals to 0. So it looks like what? It looks like ground or just 0 volts. So it's a wire. So we would just put a wire there. So we call it a short. And if you have current is 0, what does that mean? It's an open, yeah. So we would open up any current source. So remember, that's like a floating, just a wire out there. So yes, you're correct, it's just the wire. So it looks like an open. So those are what we're going to replace with the sources. Then you compute whatever variable you want, voltage or current in the circuit, using all the other techniques we've learned, KVL, KCL, node voltage, Ohm's law. And then you repeat A and B, meaning you turn off that source, turn on another one, keep going till you get answers for every single source. And then at the end, you're just going to sum up all the contributions. So summing means if you do find an answer to be negative, then you're going to use that negative in the summation. So you would have a negative value plus whatever other values. And again, if those values are negative, you would just sum up all the negatives, and then you would have a negative value. And negative for us means, if it's voltage, what does the negative mean? It's what?
Generating.
It's generating, but as far as location, if you have, okay, so maybe I should reword this. Okay, if I have a plus and a minus here and I measure across this a negative, what does that mean? Correct, the direction, it's just meaning the battery is basically in a different direction than I think. So it's a location of the voltage. So current being negative, what does that mean? Correct, it's just going the other way than what I labeled it in the circuit. Okay, so again, negatives for us mean a different thing. So we're going to see in a minute with op amps that a negative again means something else. So let's solve this circuit. We're using the superposition. So I don't remember what I said this for. Okay, so let's leave the voltage source on first. And then turn off the current source. So doing that, it's going to open up. So we see that this is open. Current is here that we're trying to find. And so if I'm going to place my ground at the same location for both of these. I'm going to place my ground here. This VS then means that this whole wire is what value? Okay, good. So this is 12 volts here. And what is current, which direction is current going in R2? Up or down? What do you notice about I1 and IR3.V? Okay, so they're going into the same node, both directions, right? So what does that mean?
Since it's open, one's the opposite of the other.
Correct. One is just opposite of the other. Since I'm trying to find IR3.V, I'm just going to say that this is the opposite. So I'm going to actually just remove it and just call this IR3.V. So what is IR3.V? Give me a hint, Ohm's law. What's the voltage across the resistors? 12. What the resistors are? So this is my pathway where current is going through it, right? So across that pathway is 12 volts. So I would use the 5K. And is the IR3.V going to be positive or negative? And it will be negative because the current is going from ground to that node. So IR3.V is minus 12 over 5K. All right, now we're going to remove the voltage source. What do we do with it? Correct, so it's just going to be a wire connecting between the two. I'm going to put ground at the same place. So what do I notice about this wire is in parallel to what? To this resistor, right? So this is in parallel to this one. So that's basically putting 0 volts across that resistor. So what's the current going through it? It would be 0 too. So I can basically ignore this one. And so I have current that I want to find in this resistor. And then now that it's not a floating wire underneath it, there's the junction of an element. This is going to be a different current. And I could label it up or I could label it down. I'm going to just call it I2. So I don't easily see like, okay, no, the voltage across it. So I don't know, I can't use like Ohm's law right away. So I always like to use node voltage. So I'm going to call this Vx. And I then have going out of this one is the 2 milli. And then I have, this is going out. So this is going to be Vx minus 0 over 2K. And then going in is going to be Vx over 3K. How do I say this? Or I could say a negative Vx over 3K equals 0. So either way, I get this equation. And then I'm going to combine. And then get a common denominator. So 6K would be a common denominator, which will give me 3 minus 2. And this will give me that Vx is a negative 12 volts. So if I have negative 12 volts here, did I do my sign wrong? 2 milli goes out, Vx over 2K. Okay, this should be a plus. this way. Okay. So equals a negative Vx over 3k, and then this becomes plus, and then this is a 5. So negative 12 over 5. So then plugging it back into this one is a negative, and then I would multiply by 3k, so this becomes plus 12 over 15k. Or simplifying it is 4 over 5k. All right, questions about solving for this? You guys following this? Coming back after a week break? Okay. All right, so now we have the two answers, and we're gonna just sum the total. Which is gonna be the combination of both. So we have a minus 12 over 5k. So IR3 is gonna be a minus 12 over 5k, and then a plus 4 over 5k. For a negative 8 over 5k. And that will be in amps. So that would be my answer. Does that make sense? Okay. All right, unit 1 practice for extra problems to practice on these. All right, Thévenin. So here is a cell phone battery pack. It has more than just the battery in there. So as you can see, there's quite a few different components within a battery pack. So it's very complicated. If I was to actually create a schematic of this, I'm going to have a lot of components. So it's going to look very, very complicated. So instead, we can model it by just a resistor and a voltage. And so all of that complicated circuitry can be modeled by this one resistor and one voltage source. So typically we'll call these a Thévenin resistor R and a Thévenin voltage V. And then we know that whatever phone we basically put on it, we can determine how much current it is drawing, or the exact voltage that is actually going into the phone. So that's usually what we want to know from a complicated circuitry, is what if we put on what we call a load, how does the current and the voltage change? And so we're going to learn this technique called the Thévenin equivalent technique to be able to reduce that complicated circuit into these two components. So when we talk about getting a Thévenin for a circuit, we're looking for these two components, resistor and voltage. And then we can put on any type of a load and model the load depending on what elements we know. So far we know resistors, so we would model it pretty much like a resistor. So this is a modeling technique. So how you do this is you first are going to remove the load from your circuit. So you identify where the load is. And then wherever the load is, you're going to put on the terminals above and below it. We would call this A and B. And then we're going to remove the load. So to find that voltage, when we remove the node, If it's not already labeled, we're gonna put ground on the bottom to make it easier. And then we are going to find what's called the open circuit voltage between A and B. And that will be our Thevenin voltage, VTH. So note that the wire here is at that top node. And then this would all be then connected to ground. So a couple different ways of finding this. You could do node voltage again and label the A point as VTH. The other is to note that the current going through both these are going to be the same. Find the current and then multiply the current times that resistor 2 to find that voltage VTH. So if I was to write the node voltage equation for that VTH node, what is that? $20. So that current would be 20 minus VTH over 40, correct? That goes in, and then this current is going to be described as, say it louder. I heard somebody saying it. VTH, thank you, over 120. So one goes in, one goes out, so they'll be equal to each other. And then we can solve this for VTH. So I just took the negative VTH over to the other side. 40 goes into 120 3 times? And then this becomes 1/2. 4 over 120. So VTH is going to be 2 into 120 is 60 over 4. Or 15. Is that right? 2, yeah. So 15 volts for the VTH. You guys' calculators do these, don't you? You just put them in the equation and it solves it? Okay. So just get used to your calculator. All right, any questions on finding VTH? Yes.
So in other problems, how are we gonna know what the load is?
So if it's not like if you're like, so most of the time you're gonna see a schematic and you're gonna be like, I need to determine where my output locations are. So you're gonna determine where those output is. If there's no load, you would just analyze it without any load on it. And then you would put A to B and not know what kind of the load is. Then once you find VTH and RTH, we'll go through then you can choose what kind of a load range you would want to have for that, depending on the application. Does that make sense? So in here, I will be very specific. There's a load. This is the resistor that's the load. And you'll know that you'll want to take it off. And so I'll be very specific in questions, or try to be at least. All right, RTH, again, you're going to remove the load, so I'm going to erase it here. Big. And again, I'm going to put A to B. And then the difference with the RTH is what we have not looked at what's called dependent sources. So if any of you have looked at some of the past exams in previous semesters, there's been dependent sources. You're gonna learn about those in the next class after this. So here we're only gonna learn about Thévenin using independent sources. So with independent sources, you're gonna remove it just the way we did in superposition. So if it's a voltage source, you're gonna replace it with what? A wire, thank you. And if it's a current source, you're going to replace it with what? An open. So voltage goes to a wire. So when I replace this independent source, I am going to put a wire because it's a voltage source. So from here now, you're going to go back to when we learned about the equivalent resistance, and you're going to take a pathway from A through the circuit back to B and find that equivalent resistance. That will be your RTH. So what is RTH here? So as I go through my pathway to get from A to B, I go to a junction and it splits, so that's going to be parallel. So you're going to have both of those pathways are in parallel to each other. In one pathway is 40 and in the other pathway is 120. And then you can see they merge again together. So that's all that's in their pathways. So it will be 40 in parallel with 120. Sometimes that might be more complicated circuitry to then get to where they join again, and you'll have to take the full pathways in each of those paths. So 40 in parallel with 120. And that ends up being 30 ohms. So this is our resulting Thévenin equivalent circuit, that 15 volts and our 30 ohms. And so now when we connect it to different loads, you're going to have different current that's going to be drawn into it. And across it, you would have different voltages depending on what value it is. So for example, if I put on a load of 60, I am going to get 10 volts and 167 milliamps. So each of these I could solve the first circuit. You know, I could go through and set this back up to solve for each one of the different loads. So this would then be all one node. And I could then solve for Vx by doing the node voltage. So this would be Vx over 120, Vx over 60. Or here, it's a little bit easier, it's just going to be, the node here is going to be, call it Vy and ground. So current going in is going to equal current going out, or I can just say that Vy is the current, which is 15 over 90 times 60. And that will also give me 10 volts. should give me 10 volts. It gives me 10? Sure. Yeah, 10 volts. So you can see it's easier when you have the simplified circuit to just find out from the load what each one of those would be. So I then know what voltage and what current, therefore I know how much power is being consumed in that device too, right? How much, if this RL was modeling a phone, how much power is being consumed here? What would it be? Do what? Correct, so you know V is now 10, right? And that current is the 166.67. Or you can just use the R, so you could do V is equal to IR. Or if you don't know I, then you could solve it for R and do V squared over R, or the other way. And you would get that the power being consumed here is 10 times 167 milli. Which is 1.67 watts. So then your circuit needs to be able to handle that much power consumption. All right, questions about this? Either of these techniques? Okay, so here's just a little bit kind of for the Thevenin, the steps to do the Thevenin, remove the load resistor, solve for VTH using any of the paths below, meaning node, KVL, KCL, current divider, voltage divider, Ohm's law. And then calculating RTH, turn off all the power sources. Current source goes to open, voltage source to a wire, solve for the R equivalent, and that equals RTH, and then redraw the circuit. And then for superposition, it's turn off each power source, or turn all of them off and turn one on. I should say turn one on at a time. And then use those techniques again, and then add all the individual values to get the total. So those are kind of summaries. Okay, so you guys get to do this one now. So use superposition here to solve for Vx.
this one, please. I suggest you need the and then try to find the answer. Because at that point, you have three equations left. So the low loss.
So we need A, B, and B.
If you wanted to do the green stuff, you could do the superposition. But superposition still kind of complicated, but it would be like a.
No, but then we
have to have like a
this,
Bible,
so we have
but
B,
that one,
B,
and this one. Yeah, I guess it also different, but like it's, you have to read all the stuff.
no, because then we have B minus B. This one is also like minus
Nobody's answered yet. So with the 2 amps on and the other one off, you should find that V3, which is Vx, is 0.62. So V3, which equals Vx, equals 0.62. So I solved that one by labeling V1, V2, V3, and defining ground at the bottom, and then writing the node voltage equations for each of those nodes, V1, V2, and V3. And I wrote next to each of the currents that I labeled what the current expression is in terms of V1, V2, and V3. And then the current going in equals current going out. So for V1 node, it's V1 over 3 plus 2 plus V1 minus V3 over 4 equals 0, because all of those are going out. At the V2 node, you have 2 amps coming in. So 2 comes in, it's equal to V2 over 6 plus V2 minus V3 over 5, which goes out. And then at the V3 node, I have V1 minus V3 over 4 coming in, and then V2 minus V3 over 5 going in, and that equals V3 over 7, which goes out. And then note that V3 equals Vx. So I could have labeled it as Vx there. So solving that gives me that V3 equals 0.62. And I used Wolfram Alpha, but you guys can use your calculators, which do the same thing. All right, questions on this first solution? So this is part 1. And then part 2 would be to solve this circuit for Vx and then sum the two together. So go ahead and take a second, if you haven't yet, to solve for this one, and then I'm going to solve it also. Actually, I don't need this if that is there. This one's a little bit easier because when you open that one up, you note that these two can be combined and these two can be combined. And then Vx is actually just this node, so I can just label it as Vx. And that solution gives me Vx is 2.6552. And so summing these, I had 0.62 plus 2.6552. It's like 3.2. Or 3.73. Ends up being about 2.7. 5, 6, 7. 8. I guess it would be 8. Rounding up. Okay. All right, questions about this one? Yes.
In the first graph you did,
Uh-huh.
why was it equals V3 over 7 and not plus V3 over 7 equals 0?
So that was just because of the way I defined, these two go in, and this one goes out. So I could have written it as a minus V3 over 7 there, equals 0. So you can define these currents going the other way, and if all of them were defined the other way, then it would be summing them. But then it would be V3 minus V1 over 4. So it would be opposite that expression. Does that make sense? Okay. All right, other questions? Okay, ready to try another one? Okay. All right, so this is going to have 3 sources. So you're going to do this technique, 3 different circuits, and then solving for Vx in this one. Okay, so solutions for the first one, if the first one that I considered was the 1 amp, so the other two, so this becomes a wire. And this one becomes an open. And so with the wire, the 12 ohms has 0 volts across it, so there's no current there, so you ignore that one. So you only have the current, all of the current has to go through that wire, because with the same idea, there's 0 volts across the 15, 10, and 5, so you have 0 current there. So your voltage Vx for this one will be 0. Does that make sense? Okay. And then if you have the 10 volt on and the other two, these two will be open as current sources. And so here they have 18 is floating, 3 is floating, so both of those have 0 current flowing through them. And I know the voltage at the top of this will be 10 volts. And so finding the current there will be 10 minus 0 over the summation of those 3 resistors, 15, 10, and 5 for 30. And then you're going to multiply it against the 15 ohm resistor. So the current of 10 over the summation of all those times 15 gives you 5 volts as your answer there. Does that make sense? Okay, seeing some head nods. All right, the third one is you have an open and then a wire, and then the 3 amp is applied. And so here you can do a current divider or node voltage. I would label this V1, so my currents are going to be, these better. So I know the 3 amp is going to be going through the 3 ohm and the 18 ohm due to the definition of a current source. The current in here is going to be V1 over 10. And the current going through the 15 and the 5 go out will be V1 over 20. And so V1 over 20 plus V1 over 10 minus 3 equals 0. And then I can solve this one for V1, and then Vx is just going to be V1 plus 3 times 18 to give me 15 or minus 15 volts. And so summing up all of those gives me a minus 10 volts. Just solve this really fast. So this is going to give me, oh my goodness, solve. V1 over 20. Get rid of this. Okay. Okay, there we go. Okay, I have an error somewhere there. Anyway, those are the steps. I'll figure out what is wrong with my math in a second. Any questions on this one? Okay, so Thevenin. So here there's no load. So just find the Thevenin between A and B. So you're first going to find the open circuit voltage. And to solve for this, you're going to want to put ground at the bottom. And then you're going to find RTH as the equivalent pathway from A to B. All right, so take a minute to solve for this one. I'm going to figure out what's going on with my math on this one. So a quick comment about the previous one. I was looking at VX on the corner here. Solving for VX3, which is across here, would be V1 over 20, and it'd be minus because the polarities. So you have the polarity of this one is a plus to minus, which is opposite the polarity of the VX3. So you get a minus I times R. So with that, it would be a minus V1 over 20 times 15, which gives you minus 15 volts. So you'd get minus 10 volts total there. Okay. All right, so for this one, find the answer. 17. All right, so finding VTH here. Again, I defined V1 as the leftmost, V2 in the middle, V3 on the right. And then each of those define the currents through each one. So current here is going to be V1 minus 6 over 4. Here is V2 over 2. Here is V3 minus 12 over 4. Here is V2 minus V3 over 2. And here V1 minus V2 over 2. This one is V1 minus 8 minus V3 over 4. So after defining each of those currents, doing a current summation at each of the nodes. So this is at V1 node. You have V1 minus 6 over 4 going out, V1 minus V2 over 2 going out, and V1 minus 8 minus V3 over 4 going out of that node. And then at V2 node, you have V1 minus V2 over 2 going in, and then the other two are going out. So V2 minus V3 over 2 plus V2 over 2. And then at V3, you have the top one coming in, V2 minus V3 over 2 coming in, and then V3 minus 12 over 4 going out. And putting that into Wolfram alpha, checking to make sure the equations are the same, is going to give a VTH of 4.4 volts. So that's solving that set of equations. So VTH will be 4.4. Yeah, I did do that. Okay, ignore the RTH of this one. I forgot that one was more complicated. So we're not going to worry about that one for now. All right, any questions? So again, you're going to learn a new technique in 2280 to solve that one. So you'll learn that technique next, a little bit more complicated technique. So. All right, see you guys on Wednesday. Remember again, if you haven't taken the quiz for today, make sure that you take the quiz. And again, the quiz attendance for today is superposition with a capital S. And if you haven't yet picked up your exams from 1220, please come and pick them up.